Thank you again for the invitation. And so I want to give you some information about the links between Motivic homotopy theory and birational geometry. So for the beginning of the talk, I'm going to roughly introduce what Motivic homotopy theory is, even though most of you already know what it is, I guess. So I'm going to fix a base field K. And I'm going to assume that K is perfect. Later on during the talk, maybe I'm going to need the fact that K is infinite, or maybe characteristic not true. So the philosophy is that this should not be some assumption. I mean, this should work in general. Even for K perfect, some theorem works generally for any fields or even any base scheme, general base scheme. So I want to study smooth schemes. And the usual construction is to force colimits in this category. So I'm going to formally add colimits to this category by taking presheaves of smooth schemes, or maybe simply short presheaves of this category. If you don't mind infinity categories, we can skip the delta, okay? And then we can force Niels-Feld topology. So we localize with respect to some topology, which is the Niels-Feld one. And we want A1 invariance property, all right? So, yeah. For me, this is important, okay? And so let's call it H. Or maybe we point this and... so this is called the unstable Motivic homotopy category of Morel and Voevodsky. And then, just to fix some notation, we can stabilize this category. So just like in classical algebraic topology, we're going to invert the sphere. So we obtain SHS1, which is the category where we have inverted the simply short sphere, the topological sphere, if you want. The one thing that is different from classical algebraic topology that in Motivic homotopy theory there is not just one sphere but two spheres. So there is the classical topological one, but also the Tate sphere or the algebraic sphere. So, and which is GM. So we also want to invert GM in this category. And this is the stable Motivic homotopy category of Morel and Voevodsky. All right, so when I say Motivic homotopy theory, I mean, well, we want to study this category, and we want to understand this, the object of this category. So usually this is way too much for us, at least for me, way too complicated. And we're going to restrict to one subcategory of this category, which we call the heart of SH. So I'm not going to define it. So we have something called the arch, and so we can, okay, let's say it's a definition, okay, and this one is the category of homotopy modules. Okay, so what is a homotopy module? It is just a functor from the category of smooth schemes over K to the category of abelian groups, Z-gridded abelian groups. And so it is a Nisnevich sheaf. And there is some assumptions such that we want some A1 invariance property. So for me, this is really important. Okay, so x and A1 of x is pretty much the same for me. And we have also some other properties like so the relation is compatible in a sense with the GM stabilization, and we have also something with the Nisnevich cohomology. Okay, so let's say I want to.
Does this description of the part require it to be perfect or not?
Good question. I don't know. I don't think so. Maybe I have to check. Yeah, so pretty much this, if you know how to define this, this description of Morel is pretty much tautological in a sense. So maybe we don't need that. But you still have to be careful sometimes. So, I mean, in Morel's paper, you have perfect fields everywhere. So, but yeah, nowadays we can do better than that. So maybe with modern tools we can skip this assumption. Okay, let's say I want to study this kind of functors. It's still way too much for me, and I want to have some equivalence with another category that I'm going to define, which is the category of Milnor-Witt cycle modules. So this is a theorem. I'm going to describe one functor of this equivalence, and I'm going to use this as a convenient excuse to define to give you a bunch of definitions. And then I'm going to define some groups, and then I'm going to say that, oh, look, this is a birational invariant, okay? Okay, so what is it? First definition, fix F a field. In practice, we are going to look at fields over K, finitely generated field over K. But let's say just any field, and we can define the Milnor-Witt K-theory of F is the Z-graded algebra with unit generated by, so we have symbols of degree 1 coming from any unit in F. So this one has degree +1. And we have one symbol of degree -1, which is like the hop map, if you want. So let me recall you the relations. So the first one is that the symbol of A and 1 minus the symbol of A is 0 for A not 0 and 1. Okay, so this is called the Stein-Band relation. The second one, we want to compute the product of the symbol A times B, and it is the symbol of A plus the symbol of B. But in this case, so if you know classical Milnor K-theory, this is just this relation. But for Milnor-Witt K-theory, we have this bit here. Okay. Then we want the symbol coming from the unit to be compatible with the eta. So these two commutes. And finally, we want some weird relation. So H is going to be 1 plus minus 1, which is 2 plus eta symbol of 1. So this is the hyperbolic map, if you want. Okay, so just to give you what it is. So if you know the classical Milnor K-theory, if you kill eta in this definition, so by definition, this is just the classical Milnor K-theory. In degree 0, this is going to be the Grothendieck-Witt group of K. So it is defined by stuff like that. F. So if you consider a unit in F, you have this quadratic form, and I can set it to 1 plus eta symbol of 1 of u, and we obtain an isomorphism. And in negative degrees, it's going to be the Witt groups. Okay, so in positive degree, this looks like the classical Milnor K-theory, and in negative degree, we have this quadratic stuff. Okay, so now I can define you what is the Milnor-Witt cycle module. So this is going to be a functor, but this time it's going to be defined over fields over K into the category of Z-graded abelian groups. And we have 4 types of data on that. So the first one is, let's say, obvious. If I take a field extension over K, I want this to be a functor, so I have some restriction map from ME to MF. All right, so nothing new. Then the next one is going to be D3, so I'm going to skip D2, sorry, just for historical reason. I want an action from the Milnor-Witt K-theory to M, okay? So the main example of a Milnor-Witt cycle module is going to be the Milnor-Witt K-theory, all right? So I want an action like that. Okay, now that I have an action of the Milnor-Witt theory on M, I can define the twist by a line. So in practice, we're going to twist by line bundles, but for this, we just consider a line, so a one-dimensional vector space over a field. And I can twist M, okay, let's call it L like that. So this is going to be another abelian groups, which is going to be isomorphic to this one, but in a non-canonical way. And I consider the abelian groups generated by the unit of E and the abelian groups generated by non-zero element of L. And the action here is given by these three. All right, so that's how I can twist my Milnor-Witt cycle modules. And why do I need that? It's because for D2, I'm going to consider a finite field extension. And I want a co-restriction map, also known as transfer map, that goes from the big field with a twist to the smaller field. Okay, degree zero map. All right. And then the last data is if I consider F discrete variation on a field, I want a map that goes from the fraction field of this variation and into the residual field. Okay, so kappa V, the residual field of this variation, and I want a degree minus 1 map. Okay, and again, I need to twist this map in order to have something meaningful. So MV is the maximal ID of V, and MV over V square is a line, and I'm going to take the dual for just reasons. And I have a boundary map like that, okay? So that's how you define a Milnor-Witt cycle module. You have a dozen of axioms that basically say that these 4 data are like compatible with respect to each other, okay? Also, this is supposed to be a generalization of Rost cycle modules, if you know what it is. But in the Rost case, we do not have any twist like that, so it's supposed to be some kind of oriented theory or GL-oriented theory. But in this case, this is not oriented, and you have to twist everywhere in order to have some meaningful maps, okay? So now I'm going to define a complex called the Roche-Schmidt complex. So if you consider X a scheme, finite tap, I mean, you could be singular, I don't care. L, line bundle over X, and M, a Milnor-Witt cycle module over K. And you can define some complex take the sum over points of dimension p, for the p here, for any integer p and q. You take the second module in some gradation. For any point you have the residual field. And then again you have to twist by some line bundle for this to be meaningful. Okay, so this is an abelian group. You can define a differential map. I'm not going to do that, but basically this comes from the fact that we have D2 and D4, so you can define some differential. And you can prove that this is indeed a complex, mostly by definition. And thus you can define its homology group.
Sorry, I have trouble parsing the complex because there's some bigrading with P and Q. So
Yes, so fixed Q. I'm going to define a complex for each MQ, okay? And then you can take the sum over any Q, okay? So this one is a complex, okay?
but it does not depend on MQ, right? It depends on M.
No, I mean, this complex is going to depend on MQ because there is Q here. But
You need the whole M, is what he's saying.
yeah, you need you need the whole M if you want. Sorry? It's just a convention. So for me, it's P plus Q by convention, but in some other conventions, some people, you want to take the other one. But yes?
Can you just sketch out how you get such a Milnor-Witt cycle module from an object?
I'm going to define the function, okay?
So your differential decreases the degree P.
Yes. So in this case, this is homological convention if you want. But you can also define a homological one and then you, yeah.
Could you please give me some examples of this sort of data?
Yeah, I'm going to define, I'm going to give you examples. So let me give you the homological complex, the homological groups, and then give you some examples. And now you can define the so-called Chow-Witt groups with coefficients in M. And just take the homology in P of this complex. Okay, so for instance, the main example that we have, okay, so let's first take the oriented example. So the classical Milnor-K theory. You can recover the classical Chow groups. Okay, let's twist by a line bundle, just for the sake of it. But it's not going to depend on that. And this is APX, the Milnor-K theory in degree minus P, twisted by something. Okay, for the classical Milnor-K theory, this does not depend on any twist. Okay, so you can take any line bundles, and this does not depend on any line bundles, and you recover the classical Chow groups. Okay, and yeah, so just by convention, I have this minus P, but if you want to take the other convention, it works too. All right. No.
Even if not necessarily finite time.
Okay, you still have to be careful, but for instance, for essentially smooth schemes, you can take the limit and define the same group from general schemes, I guess.
You need some notion of dimension.
Yes, indeed. Yeah, so I want to do this remark later, but yeah, so this is an ongoing joint work with Frank Sujin and Frédéric Desclis, and we try to do that over any base general scheme. But you do need some dimension function in order to have some. You need to sum over the dimensional p point of x in a sense. So you need this to make sense. The other example is the Milnor-Witt K-theory. And in this case, you obtain, by definition, what we call the Chow-Witt group of X, which is A, X, K, S, P. So this was defined by historically by Morel and Barge, and then studied by Jean Fazel and others. And this one does depend on the twist, okay? And if you want, in a sense, these Chow-Witt groups are like Chow groups, but instead of having cycles with coefficients in Z, you have cycles, but with coefficients in quadratic forms, okay? Because the P plus minus P is just K0 of the Milnor-Witt KDO, which is GW. So the main coefficients are GW if you want, so quadratic forms, okay? So these groups, in a sense, are pretty nice if you want to study intersection theory. So they form a good framework in order to have some quadratic intersection theory. But instead of having multiplicity that are like just basic integers, you obtain quadratic forms instead of integers, all right? Maybe another example is that, for instance, if I consider the Chow-Witt group in homological degree 0 of Pn with trivial line bundle, it's going to be, so this is a result of Fazel. So if n is even, this is GW of k, and if n is odd, this is just d, okay? So you obtain something with quadratic forms indeed, and also it is not stable, okay? So it does depend on n. All right, and for the main theorem, let's say I consider the category of Milnor-Witt second modules. Consider M, and I want to define a functor to homotopy modules over K. And for that, I consider X as smooth scheme. And I consider the cohomological in degree 0 of M twisted by some omega x. Okay, and you can prove that this is indeed a homotopy module. Okay, so in particular, if you consider the definition of a Milnor-Witt cycle modules, there is no A1 invariance property in the definition, but you can prove that these Chow-Witt groups do have some A1 invariant property. And how do you do that? It's because of the D2 data, basically. Okay, so the transfers are more or less equivalent to the fact that these groups are A1 invariant. All right.
Is this really even and odd? It's not the other way around?
Oh, you have to check. Maybe I'm wrong.
Like for P1, isn't class of a point of P1?
Okay, so maybe I'm wrong, but
Sorry.
yeah, you have to check. I'm not sure. Okay. Yeah, I will check. Okay. So one example is that these groups are birational invariants for X smooth and proper. Okay. So this result is really not surprising. But okay, for instance, if you consider just classical Chow groups or just classical Chow groups, in homological degree 0, this is pretty much trivial. Okay, so there is nothing here. But for Chow-Witt groups, then you have quadratic forms. Okay, so this group is not that trivial. And for any Milnor-Witt cycle modules, you may obtain some homotopy modules. Okay. And this also comes from the fact that these are, in a sense, unramified sheaves. Okay, so if you know what it is.
Sorry, but even in I, shouldn't be 0 adding that you have to think that you wrote first.
Sorry?
But if n is 0, then surely you must get the W of k. So
Yeah, so for 0, n equals 0, this should be just GW of k, right? It's one or the other, so.
I think what you wrote first has a better chance.
Yeah, maybe leave it alone.
Yeah.
Okay. Yeah, so you have a degree map that goes from the Chow-Witt groups in homological degree 0 of any x into GW. Okay, so you have some kind of a degree map, like cycle degree map, but just for quadratic forms. So another new result, which is more recent, is the fact that in homological degree 0, these are birational invariants. Still for X smooth proper. Okay, not just for any twist, you still have to be careful, but anyway. So just to give you a history of this result, if you consider M to be the classical Milnor-Witt theory, so this was proved in the 80s by Coulot-Helen for X as surface or any X but in characteristic 0. Okay, so when I say Milnor-Witt theory, I mean just regular Chow group in degree 0. Then Fulton proved that if K is algebraically closed, then this is true by true in the book of Fulton, so chapter 16, I guess, of intersection theory. But if you look at the proof, you can see that he never used the fact that K is algebraically closed. So, okay, so this was proved for any in any characteristic. For M, a homotopy module with transfers, so I mean Voevodsky transfers, C Markouillev, and for M equal the, so this is for oriented theory in a sense. And for not oriented theory, for Milnor-Witt K theory, this was proved. So assuming that the characteristic of K is not 2 and K is infinite. This was proved by Asok. So in this case, you have the Chow-Witt group in degree homological degree 0. And this works for any field, even if K is not perfect, in any characteristic, and for any Milnor-Witt cycle module. So in particular, we cover this. Okay, let's go. So now I want to give you some links between Motivic homotopy theory and, well, birational geometry. So in birational geometry, people are interested in, well, they want to know if a scheme is rational, 2Pn, for instance. They want to know if a scheme has a rational point. And one notion that it is useful is the following. So it's going to be a definition / theorem. X is going to be smooth, proper over K, and K is going to be infinite of characteristic not 2. Okay, and if I forgot, let me quote again the work of Asok. Okay, he did pretty much everything. So you have this notion of X as having a 0 cycle of degree 1. Okay? So by definition, what it is, it means that if you consider the classical Chow group of X, you have a degree map to K, which is just Z, and you wonder if you have a section, okay? Split. And in other words, it means that there exists L1, Ln, finite extension over K, such that the GCD of the degree of Li is 1, and such that for any extension, we do have a point, a rational point in this extension. Okay. So this means that we almost have a rational point in X. Okay. So this is just folklore or definition if you want. Okay. On the other side, we could have the same definition in a sense. X has I don't know how to say that, let's say quadratic, 0 cycle of degree 1. So let's say we can define this like that. So we have a quadratic degree map from the Chow-Witt group in homological degree 0 to GW of K, and we want this to be split. And there is a way to.
Isn't it split subjective if no one could?
Yeah, it's selection. Yeah. So.
I mean, but subjective implies it's a map of GWK modules.
Yeah. What do you mean?
Well, GWK is a projective GWK module. So. Doesn't every subjective? Well, never mind.
Comment is split is equivalent to its surjective here. It was in
Maybe not. Okay. Fine.
Not sure. No. I mean, you could have some point of. I mean, even in the classical case, you may have some X without any degree 1.
Map of a Abelian group size, Z is split. Z is a projective Z module. But never mind.
Okay.
Whatever. It doesn't matter.
Okay. Yeah, it doesn't matter. Yeah. So I want to give you some definition of that in a shiftify way. Okay, and that's why I put this over. Okay. Okay, just to fix the notation, in this category, you can define, just like in classical algebraic topology, you can define homotopy groups. A pi naught A1 of X, which by definition is the Nisnevich shiftification of something like that. And likewise, you can define a S1 stable pi naught, and also a S1 A1 pi naught in these categories, okay? So now I'm going to use this sheaf just to give you another, definition or equivalence if you want, to the fact that X has a quadratic zero cycle of degree 1. So you want this sheaf, and you have a canonical map to the pi naught of K to be a split AP. And this one is just GW if you want. Okay, so you want something like that. Okay, and if you know what is Suslin homology, you can have pretty much the same thing here. So by definition, these three are equivalent, and let's say these three are equivalent. And this is a theorem of the work of Hassok, in a sense, that these are equivalent. All right. And now let's consider another result of Hassok. So let's X smooth proper. X has a rational point if and only if this sheaf, so the S1 stable sheaf of X, is split AP. Okay. So why do I care? Well, in birational geometry, we often ask whether or not, assuming that we have a zero cycle of degree 1, does X has a rational point, okay? So this is an old question, and the remark was done when I was still a young teenager playing video games. So it's in a paper of Levin, an old paper of Levin, where he does the following remarks.
Just a silly question. So how do you compare this with Brouwer-Manning obstructions? Is it stronger?
I don't know. So okay. So just to repeat the question, there is this notion of Brouwer-Manning obstruction in birational geometry, and there is huge conjecture about this type of obstruction, which is supposed to be the obstruction of whether or not X has a rational point, in a sense. And I don't know if there is a Motivic version of this, but this is a good question. Yeah. Okay, so let's take X a nice S1 spectra. So in SHS1, we have functor of the P1 of GM suspension. And if I consider, so this is a junction, and so if I can take X S1 spectra, I can have this map. Okay, I can reiterate this process and get another map like that. Etc. And for any n of this map like that. And then I can take the pi naught. Okay? So the S1 stable pi naught. Okay, and the S1 stable pi naught. And then I consider the colimit over this. And I obtain the P1 stable pi naught. Okay? So, and of course, we have maps to pi naught S1 of k, likewise of k, the same of k, etc., 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 to the pi naught SA1 of k. So with this diagram, on the right, you have information. If you consider split AP of this map, you have information about quadratic zero cycle of degree 1, or just zero cycles of degree 1. And if you consider split AP here, you have information about whether or not x has a rational point, okay? Assuming that x comes from a nice smooth schemes, okay? And so this was remark by Levin, also in the work of Asok. And recent results prove that, so let me write that here. So the question is, how do you compute this? And how do you relate this to the first group? And in fact, you can do that in a sense. So theorem, so this is a baby Motivic Freudenthal theorem. Okay. For n greater than 2, we have isomorphisms. Okay, and so this was proved by Barman, and I did a little bit improvement of this result. Okay, so like that, and I also proved that. Okay, so also thanks to Barman. Yeah, I mean this map. Okay, so yeah, I mean and GM X 2 plus 1. Okay, I mean this map. So let's call it theta m. Then theta m. All right? And for n greater than 1, this is true if you forget torsion. So if you tensor by Q, then it should be true, and in general, or if so, you have a conjecture of Morel on transfers is true. Okay, so I'm not going to say that, but in a sense, if we have enough transfers, then this should be true for n equals 1. But for now, we only know that this is true for n equals 2, okay? Okay, so let me conclude. So it is expected that should be true here, okay? But if it is not true, this would mean that a split AP of this map would give some kind of birational invariant, which should be between the fact that X has a 0 cycle and between the fact that X has a 0 cycle of degree 1, okay? So this is kind of weird. Maybe it exists, but it is expected that this one should be just the same as this one. So you have information about the fact that you have a 0 cycle of degree 1, okay? And well, just to conclude, you have lots of conjectures. For instance, you have a question of Serre. If you consider principal homogeneous spaces over G nice algebraic group, and you assume that X has a 0 cycle of degree 1, then the question is, does X has a rational point? And I'm not saying that I can prove this conjecture of Serre, which is really hard, but we at least have some reformulation in a Motivic language, in a sense. Thank you. Yes?
Have you thought about the non-abelian version of this story? What's the sort of thing which would be pi 1 of a Motivic space?
No. Just before I forget, Tom Barman, Asok, and Hopkins, they proved a general Motivic Fountain theorem this year, so you have a better result. So about non-abelian stuff, I don't know. Wait. Well, yes, so if you consider just pi naught A1 instead of SS1, then let me write it here. The pi naught A1 of X smooth proper, if you take the evaluation at a field over K, for K perfect, let's say, then you obtain the R equivalence of A. Okay? So in a sense, you do have information about rational point already in here. Okay? And so yeah, it's pretty related too, in a sense. But this one is far from abelian. It's not even a group in general, and I really don't know.
That's the unstable. Which pi naught is that? Sorry.
Yes, this is the unstable one. Yeah. Yeah, if you only know classical algebraic topology, so usually you have the connected component of X. Here you have the free group generated by the connected component of X, and then you have the free abelian group connected of X. But in this case, it is already abelian because it is stable. Okay.
So just a silly question. So I didn't, maybe you've already covered that, but I didn't get, I mean, how you characterize, I mean, rational, like what, birational equivalences, I mean, you have a theorem, but you didn't, I didn't get how you characterize that birational equivalences in terms of, for example, this more coherent word, I mean, this how to say, this motivic word.
I'm not sure I understand your question. How do you prove that? You mean? How do you?
No. Previously you mentioned theorem. If I remember.
The fact that Chow-Witt group are birational invariant. You mean?
Yes, something like this. I mean, I didn't get how you I mean use this.
I don't. Sorry. So the previous results about Chow-Witt groups with coefficients in Milnor-Witt modules is not strictly related to this one. If it is your question.
No. I was just asking how you play with this concept.
Carefully.
Yeah, you play carefully with this concept. Yes.
Is the case n equals 1 here known if you take the field k?
I don't know. So if you consider k, so this sheaf can be computed in a sense. Let me write it down.
It's not z?
Yes. So yes, it's z. But
And the next one?
But this one could be also, you can, okay, again, let me write it here. So, okay, okay, maybe I'm wrong because it's not clearly stated in ASOC. But I guess for X smooth proper, the SS1, the pi naught of SS1 in L, this should be the free abelian group denoted by R equivalence. L. That's why you have rational information in that.
So there's potentially something between this and GW. Okay.
You mean for n equals 1? I mean, it is expected that this one should be this one because of Morel conjecture. In a sense, if you do have transfers, yeah, but if you consider Q coefficient, this is true. So, and I would pretty much, I mean, when I talk to experts in birational geometry, they don't know any intermediate statement between the fact that you have zero cycle of degree 1 and rational point. I don't know any in-between statements of that. So it would be nice, but I don't expect that we have one. So.
Tricky question. So, what pi 0 is 1, which how to understand this invariance? By some geometry.
How to understand this pi naught?
Yes.
It's pretty hard. Yeah. So as far as I know, it's not really well studied. The S1 stabilized. Usually, we only work with P1 stabilized stuff in Motivic homotopy theory, and this one is kind of in between and weird to work with. So, yeah, I don't know.